Welcome to the Deep Dive. We're here to give you the shortcut to understanding complex topics.
And today we're tackling carbon dioxide removal, or CDR.
It's been 9 years since the Paris Agreement, and the science is pretty blunt now. Staying below 1.5 or even 2 degrees Celsius means we absolutely need these negative emission technologies.
It's not just about cutting emissions anymore, though that's still priority number one. We also have to actively pull CO2 out of the air.
So our mission for this deep dive is clear. We're digging into a key study called Navigating the Obstacles of Carbon-Negative Technologies.
Right. It lays out the huge challenges, political, technical, economic, you name it, facing CDR.
And this study really hammers home why this is so urgent right now, doesn't it?
It does. They've crunched the numbers. As of early 2024, our remaining carbon budget, and this only gives us a 50-50 shot at 1.5 degrees, is just 210 gigatons of CO2.
Okay, 210 gigatons. To put that in perspective for you, a gigaton is a billion tons. So 210 billion tons left in the budget.
Exactly. And think about this. We're currently emitting around 40 gigatons globally each year.
Wow, so simple math says.
Yeah, that budget is completely gone by 2029. If we keep going like this, we just run out of road.
Which means we need, well, practically miraculous decarbonization, super fast.
Cyclical plus CDR at a massive scale, they have to happen together.
Okay, let's unpack the biggest, maybe the most dangerous mistake people make with CDR. That idea that it lets us off the hook for cutting emissions now.
The "we'll clean it up later" fallacy. Yeah, this study pushes back hard against that.
So how should we think about it then?
Well, the study frames it very clearly. CDR is a separate process. It's not a substitute for stopping fossil fuel use.
Yep.
Its main job is dealing with legacy emissions, all the CO2 already up there, and the residual emissions.
Residual meaning.
Those really tough sectors like aviation, maybe cement making, shipping, the stuff that's incredibly hard to decarbonize completely, even after we've done everything else.
So the study suggests a kind of dual approach.
Exactly. It says we have to act like there's no CDR when we're focused on getting rid of fossil fuels.
But at the same time,
We have to research and scale up CDR, like we still want to hit that 1.5 degree target. Both are essential.
that really highlights the scale problem, doesn't it? Because where are we now with novel CDR capacity?
Tiny. The study points out we're removing maybe 1.3 million tons a year right now with these newer technologies.
1.3 million tons versus 40 billion tons of emissions.
Yeah. And the study uses this great analogy. It says our current CDR capacity is like a time machine that takes us back only 17 minutes in a whole year.
17 minutes.
Yeah.
That's sobering.
It really puts it in perspective. Priority 1, 2, and 3 have to be stopping the emissions at the source, ending fossil fuels.
But given we do need to scale CDR massively from 17 minutes back to maybe years, what does this study highlight about research priorities?
A lot of focus goes on the research gaps, especially for things like marine CDR ocean-based methods.
Well, I'm
Because the potential scale is huge, possibly billions of tons of removal. But there are massive unknowns,
like what?
like measurement, reporting, and verification MRV. How do you track CO2 stored deep in the ocean reliably and affordably?
Right. It's not like sticking a monitor on a pipe.
Not at all. You need sensors, complex models, and without solid MRV, you can't get permits. So the study really calls for government funding first just to research the MRV and get permits for field trials.
Okay, let's shift from the big picture to the nitty-gritty, specific technical problems. The study looks closely at direct air capture with storage, DCS.
And it identifies what it calls 3 key adversaries that DCS needs to overcome to be viable economically.
Adversaries. Okay, what are they?
Basically, resource issues and stability problems. They boil down to water, variable conditions, and material degradation.
So let's take the first one, water. How is water an adversary? Seems counterintuitive.
Well, it affects DCS in 3 ways. First, humidity in the air competes with CO2 for the sorbent material. Second, you often need steam or heat involving water to release the captured CO2 for storage. That takes energy.
Right.
And third, water can be a byproduct you then have to manage, so it hits energy use and overall efficiency.
And does that link to the second adversary? Variable conditions?
Absolutely. Humidity, temperature, even air pressure, they all change constantly, daily, and seasonally.
So a DAC plant performs differently on a hot, humid day versus a cool, dry day.
Exactly. If you're capturing material, your sorbent is optimized for one condition, its efficiency drops when things change. That instability makes performance unpredictable and generally lower over time.
And the solution there is?
Better materials, basically. Sorbents that are robust across a wider range of real-world conditions. Choosing the right tech for the right climate.
Okay, and third adversary?
Material degradation. Simple wear and tear, really. The sorbents or solvents used to grab the CO2 just break down over time.
Like anything, I suppose.
Sure, but it means your capture efficiency goes down and your costs go up because you have to replace those materials more often. Getting longer-lasting, stable materials is key for scaling up economically.
All right, let's switch gears to the other big category, land use. Often called affowill agriculture, forestry, and other land use. Planting trees, basically. That's often seen as the easier option, right?
It's certainly the most mature. We know how to plant trees, but it's got its own major challenges. This study really emphasizes prioritizing reforestation over afforestation.
What's the distinction there, and why does it matter?
Reforestation means restoring forests where they used to be. That usually brings back habitat, helps biodiversity, lots of co-benefits.
Okay.
Afforestation is planting forests on land that wasn't previously forested, like grasslands. That can actually harm existing biodiversity or really strain local water resources if it's not done carefully.
And there are specific geographic hurdles, too, aren't there? The study mentions Brazil.
Yeah, in Brazil, you run into high land opportunity costs. Cleared land is often worth more economically than forested land, which is a disincentive to reforest.
Huh.
Plus, there are legal complexities. Once land is reforested, rules might kick in preventing future clearing, which makes landowners hesitant. And, of course, increased wildfire risk is a huge issue.
And China. They have huge tree planting programs.
They do, and they've been successful in building a carbon sink. But the study points out that sink is likely to decrease in the coming decades just because those forests are getting older. They absorb less CO2 as they mature.
So they're running out of space, or?
Well, new planting is getting pushed onto more marginal lands places with water stress, poor soil, which makes success harder. And fundamentally, we still lack really good models to predict how these forests will grow, die, and respond over time.
So whether it's DCS or a forest, you can't just look at the technology in isolation.
No, you absolutely need a systems view. The study calls for using prospective life cycle assessment, or LCA.
Prospective LCA.
Yeah, prospective, because these things aren't fully scaled yet. We need to model the entire impact upstream and downstream.
Give me an example.
Okay, say you build a DOS plant and power it with new solar panels. Sounds great, right? Clean energy.
Seems like it.
But building those solar panels required mining materials, manufacturing, transport. That has its own footprint upstream. A prospective LCA tries to capture all of that.
So it's about integration, looking at the whole industrial ecosystem.
Precisely. Can you use waste heat from a nearby factory? Can you reuse water? How does it fit into the local energy grid? You need to ensure the whole chain is genuinely carbon negative, not just shifting burdens around.
Now, I have to bring up the energy question, because this is always the big one people raise about DOS, the sheer amount of energy needed. It feels like a showstopper.
It does, doesn't it? It's the elephant in the room. But here's where this study offers a really powerful counter-narrative.
Okay.
It argues that the energy demand, while massive, is not the fundamental roadblock people often assume it is.
Really? How can that be?
Their calculations suggest that even hitting a super ambitious 1.0 degree target, which requires enormous CDR, might only increase total global primary energy demand by around 10%.
Only 10% for that much CDR.
Yeah. And crucially, they project that this extra demand can largely be met by solar PV.
Because solar is scalable and getting cheaper.
Exactly. It's scalable, the cost keeps dropping, manufacturing is booming, it pays back its own energy footprint quickly. So while the energy number is big, the source of that energy looks manageable. The study concludes the real bottlenecks aren't energy supply.
So what are they then?
Technical stability, like we discussed, cost definitely, but also policy, regulations, and crucially, social acceptance.
Okay, let's dive into that social side. Because scaling any big industrial process, especially a new one like CDR, isn't just about engineering, is it?
Not at all. It's a huge social challenge, and this study highlights a major risk called perception spillover. Imagine one CDR project somewhere, maybe a forestry project or an ocean project, goes wrong. Maybe it fails environmentally or doesn't deliver the promised carbon removal.
Okay.
That negative perception, even if it's about a completely different type of CDR project hundreds of miles away, can poison the well for all CDR projects. People hear CDR failed and oppose the DOS plant planned for their town.
So bad news travels fast and taints everything.
Exactly, which means public engagement has to be incredibly robust and meaningful from the very start, especially engaging communities that have, historically borne the brunt of industrial pollution or development.
And that engagement needs to be more than just trying to get buy-in for a tree-cooked plan, right? The study talks about co-design.
Yes, co-design is presented as the ideal. It's not about selling a project to a community. It's about genuinely working with them to figure out the trade-offs, the uncertainties, the benefits.
So the community helps shape the project itself.
Ideally, yes. The most transformative model discussed is where community groups actually take active roles in owning, designing, and governing these projects locally. That builds real trust and local benefit.
That feels like a world away from how big projects often happen now.
It is, and this challenge gets even bigger when you look at global equity.
How so?
Well, the study notes that a lot of the potential for large-scale CDR-suitable land geological storage sites is located in the Global South.
Makes sense.
But almost all the research, the funding, the technological development is happening in the Global North.
That creates a real imbalance.
A huge one, and it can lead to problematic situations. The study gives the example of Japan.
What are they doing?
They're exploring plans to capture CO2 in Japan but then ship it to Southeast Asia for storage, partly to avoid local opposition at home, especially from fisheries concerned about coastal impacts.
So basically exporting the potential risk and burden.
Pretty much, and that's likely to create major acceptance issues in those receiving countries. The study argues the only fair way forward involves empowering people in the Global South to lead and make their own decisions about CDR deployment in their regions.
Okay, let's pivot to the money side specifically. Carbon markets and offsets. These are often presented as this clever way to reduce emissions cheaply.
The ultimate have your cake and eat it too policy, supposedly. Lower costs for polluters while getting climate benefits.
But the reality,
As this study points out very directly, is that a huge chunk of carbon credits generated historically just lack integrity. They don't represent real additional emissions reductions.
why does that happen systemically?
It's a fundamental incentive problem identified in the study. For the most part, neither the buyers nor the sellers actually care most about the environmental quality of the offset.
What do they care about then?
The tradable credit itself, the piece of paper or the digital certificate that allows them to claim compliance or make a green statement.
And that creates a dilemma for regulators.
A massive one. They face pressure to ensure there's enough supply of credits to keep prices low and buyers happy. This often means prioritizing quantity over quality, leading to a race to the bottom in standards, whether it's in regulated compliance markets or voluntary ones.
So can these markets be fixed? Better rules, better accounting?
The study is quite pessimistic on that front, based on history. Attempts at stronger governance have rarely delivered significant, lasting improvements. And it notes something quite telling. When the carbon market industry faces scientific criticism about credit quality, their responses often mirror tactics seen in science denial.
Like what?
Dismissing critiques as flawed, maybe attacking the researchers, or constantly claiming the market is still nascent and needs time to mature, even though carbon trading concepts have been around for over 30 years.
So the conclusion is pretty stark then.
Yeah, the study concludes that carbon markets, as currently structured, risk becoming just another way for society to delay the real hard work of decarbonization. They become an excuse not to cut actual emissions.
Which means we need more than just technical fixes for markets.
Definitely. We need social science research to understand how these markets are actually being used and to design them so they genuinely drive abatement, not delay.
Okay, we have covered a massive amount of ground here, from the ticking clock on the carbon budget
Down to 2029.
to the specific technical adversaries facing discarrius like water and material issues, the complexities of land use,
The critical need for genuine social co-design, not just buy-in.
and the deep integrity problems plaguing carbon markets.
But to end on a slightly more constructive note, the study does touch on economic viability beyond just disposal.
How so?
By emphasizing the potential to create actual products from captured carbon, carbon-negative products.
Right, so not just burying CO2, but using it.
Exactly. If you can create valuable materials, you create a sustainable economic driver for CDR that goes beyond just relying on carbon prices or subsidies.
And that leads us to our final provocative thought for you, building directly on this source material. What if we stop thinking about CDR primarily as waste management.
And started thinking about it as the foundation for a whole new carbon-negative economy.
Imagine using abundant minerals and captured CO2 to make building materials, effectively locking carbon into our infrastructure, or creating specialized carbons needed for things like batteries.
If you can make those products using renewable energy, and they're cost competitive with the old fossil fuel-derived versions, well, that changes the game, doesn't it?
It flips the script from just managing a problem to actually building something new and potentially sustainable.
That's the long-term vision, integrating economic benefit with climate necessity.
A huge task, but a necessary one. We've been doing a deep dive into the challenges and pathways outlined in Navigating the Obstacles of Carbon-Negative Technologies.
Thanks for joining us.
We hope this gives you a clearer picture of the complex road ahead for CDR. See you next time on The Deep Dive.